The divergence groups have the Bowen property, paper by Bishop, pronounced mathematics, and presented by Asatryan from Yerevan State University.
Still, yes.
And yeah, it's a tough paper, huh?
Yeah, it was. I mean, I will present it as much as I could have understood it. So, may I start?
Yes.
So, firstly, I would like to thank the organizers for letting me to speak during this conference. This is my first English talk, and for the matter, this is my second talk at all. I only had one talk in my bachelor's thesis, and I'm really far away from the topic. So if you see any mistakes, please, all remarks are highly appreciated. So let's start. Firstly, I would like to make some definitions that will help us throughout the process and will give the setting. The first definition is Kleinian group, which is a discrete group of isometries of hyperbolic three space. I think we already mentioned what is hyperbolic three space, but just in case, it's the 3D analog of hyperbolic space. Just those two are models that will be used interchangeably. Fusion groups, if I'm making the pronunciation correct, is just a Kleinian group which fixes the unit disk. So two examples, one example of a fusion group, which is just the group of matrices with two matrices with integer. What? Kleinian, okay, of integer entries, and a group that is Kleinian but not Gaussian, a group of matrices with two matrices with complex integer entries. The discreteness of both groups, I guess, is arithmetic property just, and the second group is not fixing the unit disk. Deformation is a conformal map that with this relation, if we do it on both sides, gives us a Mobius for every G from the initial group. Yeah, conjugation for initial group. If we conjugate it, it gives a Mobius map for every G in initial group. And quasi fusion deformation is just deformation. P is called quasi-conformal if we extend it if it can be extended quasi-conformally to the plane. Three more definitions and that's all. So we call J divergence type and convergence type correspondingly if this sequence, in which case the distance here is hyperbolic distance, is convergent and divergent respectively. So this is one relation that will be used later. That is that we can compare the hyperbolic metric with non-hyperbolic, and here this sign means that if we divide this part to right part to the left part, it is far from zero and is bounded from above with some integers. No integers, real numbers. So we call infimum of S for which this sequence is convergent, non-convergent, divergent, Poincare exponent. And here is one, and we call first kind if the limit set is the whole circle. So here is one known, I mean, for some of you, maybe known inclusion that here it is, compact confinement divergence understand. So let's go to the Bowen property and the main article. Bowen property is the following. A Fuchsian group J has the Bowen property if the limit set of any quasi-conformal deformation of J is either a circle or has Hausdorff dimensions strictly more than one. A bit of history. So in 1979, the property was firstly introduced by Bowen, who proved it for compact Fuchsian groups. Sullivan later extended it to cofinite groups, and Astala and Zimsmeister, Zimsmeister, proved in 1990 that it is false for convergence type groups. Thus, we leave only one group of only one type of groups that we are interested in. Those are infinitely generated divergence type groups, which in this paper Bowen addressed and proved that all of them have the Bowen property.
So this limit set of the deformation, so you just take the several times, so what does it, in what sense limit set?
So what you do is you, like, the usual case in your usual model, you take a point, you look at its orbit, and then the orbit accumulates on the unit circle. So you forget about the orbit, you look at the limit, that's called the limit set. Now you deform it.
And look at the orbit once.
You deform it, and when you deform it, you get another discrete subgroup now of the group of Mobius transformations which do not necessarily fix the circle. And they turn out to be, they have to be some sort of, turns out they have to be quasi-circles.
I guess I can give here. So if we take the orbits and deform it, we come up with some other boundary. And if I understand it correctly, if the deformation is bad, if it not, if it is not Mobius for divergence type groups, we come up with something that is too strict and this has dimension higher than one. So the limit is limit of orbit. Yes.
Maybe if I want to say just one thing, just if you want to think about like this, if it didn't happen, the idea is that goes back, I think, all the way to the pattern or planning of folks, that if you have a corner at some point, then because this group like takes this corner and propagates everywhere, it kind of forces the curve to be fractal. And that's why that's easy to see in the full compact case where you have the fundamental domain is inside those things. And that's what I think a lot of that Bowen showed that in fact, not as this, I think Poincaré showed already that it has to be then non-rectifiable. But then like Bowen proved it that then it has to be not just non-rectifiable, but dimension greater than one. Then what Sullivan did is he said, let's generalize this a little bit and allow this fundamental domains maybe have a cusp, but still have finite alias. And then it's truly still that case. And this is a little bit further generalization, which is the divergence, like going from one. So it's also all the surfaces generalizing the compact case where you still have the boundaries quite small.
Okay.
Okay. So if combined with previous results, this result gives us a complete story, I guess, because what we claim is that divergence groups are divergence type of Bowen property. The theorem is not strict. The theorem one of the article is not strictly saying that. It says that the Poincaré exponent is greater than one, but we should before that prove that a dimension is greater than equal to Poincaré exponent. So this combined with the result of Astala Zinsmeister gives us that having Bowen property is equivalent to being of divergence type. At the end, I would like to ask one question about this. So to prove the theorem, we should maybe reformalize it. And Corliford does exactly that of the article. Basically, we use this property. Okay, I got too far. We use this property and theorem that and a lemma that states that in the definition of dimension, this part can be bounded from two sides by distance, Euclidean this Euclidean distance. Like we use my notes for exercise of the lemma. So by the relation I showed before, we translate this part to 1 minus g x squares, and we use this combined with the lemma stating that we have such a relation. To the boundary. Oh my God. To get the corollary. So in my understanding, what does this corollary provide us? And also we use, I guess it's a result of Cope's-Quarter theorem. We translate these distances to this part. So what gives this corollary to us is that initially we were living in a 3D space, and now we are, okay.
Sorry, I just missed, what is your UP?
What? P. P is the transformation, the action of group, I guess. Deformation. Yeah, P is the deformation. It's conjugation of.
Okay.
Okay. So what the corollary gives us is that we work on a unit disk, I guess now, not in the 3D space. So it's enough. So what we need to show now, we need to find some s greater than 1, for which this sequence is divergent. And for that, it's enough to show 3 of orbits like this. Each of the elements has finitely many distinct children, such that these two properties hold. The first one just gives us the first one tells us that the distances between children and parent are not that far, and the second one forces the sequence to diverge. And the article is about how we construct this tree of orbits. Basically, it is being on 2 lemmas. The first one, to state the first one, maybe I should give a definition of Carlson squares. Carlson square is for an arc of E on boundary, we make a square which is the square that is projected, that is created by the projection of radial projection of points. So maybe here these lines are not that good reason. Those should be something like this to point it to the center. And with some with a length of E, we define as TQ the upper half of it. And the lemma 5 of the article states that in this kind of squares, we can find children that are not that far, that close to the boundary, and have the property that will force us to have the divergence. Precisely, so let's suppose J is a divergence group, we give the Carlson square, and these two conditions are what I told. The first one is about, the second one is about being not too close to the boundary. And the first one is the property that will force us later to have the convergence. So basically, the way it shows, the way statement goes is that we can construct many disjoint Carlson squares in the initial Carlson square and find the children in the upper halves of those Carlson squares. This lemma I will not, I will just give it without proof because it is no, by the time Bishop wrote the article, it was a no result. The main contribution to the build was the next lemma. Here, see that the lemma is not requiring those children to be orbit points, just some points. And next lemma will force us to find orbit points here near the 3 points that we constructed with, let's say, minimal loss. So here's the statement of the lemma. What it gives us that near the 3 we constructed in the previous lemma, we can find orbit points. And I mean, I think that the meaning is what I exactly said. So if we had compactness, we would have this epsilon for free, let's say, from compactness. And in this case, epsilon should not depend on z, and compactness would have given us that property. However, in this case, we don't have that. And if the part with 3 stroke is removed, we also will have the relation would have been easy to find, but the main difficulty was to have both parts, the epsilon independent of z, and the derivative part also in the Fischer part also in it. So the proof goes as follows. Let's firstly say why this is enough, why these two lemmas give us the proof. So what we do here, we take m as epsilon half for each point, and then apply the next lemma, creating the 3 of orbits already, which satisfy the relation, these two relations, which result in the theorem above. So the proof goes as follows. This part was most complicated for me. I would try to explain it as well as I can, but maybe Mr. Akokan will do it even better. So we take a convex hull on omega in the Bowen model, and on the dome of this convex hull, which is just the boundary part, I guess, with a metric that is defined on the dome, not in the ball, there is isometry from this part to the dome, and that isometry gives us this epsilon being uniformal for free in some sense. The details can be found in the article those are technical. So basically what is done in the article, we take the initial disk, we go to omega, then we go to the convex hull, then we construct convex hull, go to the dome, and then we come back to the disk. And basically that allows us to find the orbits. And here are the steps how those are done. As I said, we go from Coulson squares to the, I said the steps, those are just the details, some part of the details. And I think that's it. Thank you. If it wasn't too short, I mean.
It's okay.
Yeah.
We had a long day today, so.
Yeah. Thank you very much. Questions are welcome. I am not sure I will answer them. Yeah.
Any questions? Oh.
Okay, so I had one question. Basically, what remains here to do? I mean, when I read this part, I get that in some sense all the possible cases are somewhat covered. What is done now in this field, like about Bowen property or something like that?
Okay, so the reason we chose this paper is relates to this thing that I talked about in the beginning, which was what happens to the ground motion on the surface. Like, does it go? Is it transient? Is it recurrent or not? What is is that's another characterization. This divergence property turns out to be equivalent to how you know that ground in motion on the surface is recurrent, which is the same as saying that there is a Green's function and all those kind of things. So if you formulate the problem like that, then there's lots of questions. But if you formulate it in terms of the Hausdorff dimension strictly increasing, I mean, I can tell you one problem, but here is one thing, which maybe I should tell you what was the problem or related problem to what Bishop gave me as a PhD problem, which I never did. So this is I assume I already all of you know what's a Kleinian group and what's a Fuchsian group, right? So
Correct pronunciation was Fuchsian.
yeah.
You got close.
Yeah.
Like it wasn't.
So I mean these are both names
German
given
names.
given by Poincaré. Neither Fuchs invaded nor Klein invaded. I don't know if you know the story, that the story goes by so Poincaré, actually that's one of his most famous discoveries. He discovered that the isometries of the hyperbolic space were actually the same as the Mobius transformations, right? Then he used that to define the Fuchsian groups. So when Klein read it, he got angry because he was also working on it. And then Poincaré extended it to three dimensions and called that Kleinian groups, so that the Klein doesn't get too mad. So he invented both, but they're not called by the name. Anyway, so the Fuchsian group is a group of Mobius transformation, so that when you look at the limit set, meaning if you pick a point where the group acts kind of in a way where you can take subsequences in a normal way, then you pick a point and you look at the orbit, and the orbit converges to a curve, right? So if that curve is a circle, it's called a Fuchsian group.
So essentially the dynamical problem, you start
It's a
from
dynamical
points
design.
and then you start to look on the orbit, and then you look what is the, what you have.
Yeah, and you can look at it from 2 points. The point you can take either inside the hyperbolic space, then that would be this point, or you can put it from the sphere itself, and that turns out that essentially you get the same thing. So in one case, you look at this point, and you look where it goes on the sphere. So that it gives you the limit set of the Kleinian group, or you can look, so if you like do it here, you still can get like a dense set of things. But if you start from somewhere, what's called the ordinary set, the complement of the limit set, you converge to this thing here. So now one way is when you get like the limit set is a curve, so that could be a circle, or it could be if your surface, if your quotient is kind of a surface, then you get a what's called a quasi-circle. Now, if you do other examples, you can get things like which are more interesting. So you can get even Sierpinski carpets. Okay, and one of the things you get here is that no matter how you deform this, the dimension cannot go down. It's one already. The Hausdorff dimension of any connected set is at least one, so it cannot go down, right? But that's not true in this case. If you have a limit set whose Sierpinski carpet, then in general, an image of a Sierpinski carpet can have dimension, Hausdorff dimension, any number up to 1. So here's a question, which is kind of a generalization of this thing. Now start with the Kleinian group, whose limit set is the Sierpinski carpet, so that all the complementary components are actual circles. Now deform it. It's quite possible that all the boundary components become quasi-circles of dimension bigger. Can the whole thing become smaller? So that's
You deform it and then you look on the
on the dimension. So you look at the dimension, Hausdorff dimension on the limit set as a function on the space of possible deformations. It's also related to things like volume of the convex core and things like that. So then you look at this thing, is it possible to make it down? So this thing, the limit of this thing is a number. The Hausdorff dimension of this limit set is a number that's strictly greater than 1, so potentially it could go down. So a question is, if the boundaries are circles, is that already the smallest that you can have? Or can you make it smaller? Just to connect it to other similar problems, here is a question. You start in a plane with a carpet, something that looks like this, and you can ask, can you find a quasi-conformal mapping of this circuit carpet to something else which has Hausdorff dimension less than its dimension? And the answer is yes. You can map. In general, there are things which you can map to even things where the boundaries are squares, where the dimension here is smaller. So that's yes. That follows from Hong's theorem, essentially, uniformization for carpets. But in the case of the dynamical and kind of natural situation, I think that's kind of related to the mitosis problem, which I never solved. And I don't think it's just to answer your.
That's a known problem now.
Yeah, that's enough for me, and yeah.
Yeah.
Well, yeah, so that's related to what you're saying. So can you make the dimension go? But this is more interesting in terms of topology, because the quotient here is a much more interesting manifold. In this case, the manifold is just the surface crossing the interval. In that case, it's not. So there isn't much progress, but there is an obvious problem there.